All right, so we're going to continue our discussion of the product rule and quotient rule. So past two videos, we covered those two rules. Here, we're going to do two of our familiar exercises. The first here, example 2.3.3, we're going to find the equation of a tangent line at a specific point. And then the next one, we're going to find where there are horizontal tangent lines. So these are two very important processes that the reason I'm doing these two examples over and over again is because this is super important for you to be able to do. We always want to know how to write the equation of a tangent line. That's a very big deal in calculus. That was one of the major catalysts for inventing calculus, was to find the equation of a tangent line to find the slope of a curve. And then the second question here, finding where there's horizontal tangent lines, that's going to be super important for curve sketching and doing lots of stuff, finding extrema throughout this chapter and next chapter. So let's hop in here with the first one. Determine the equation of the tangent line of f is the product of two functions. That's the important part here. We have x squared plus 1 times x minus 2. Now, I suppose this is one of those examples where you could multiply out, you could FOIL and avoid using the product rule if you wanted to. But here, I'm going to use the product rule since that's where we are. So let's see. We first need to find f prime, because remember, we have a couple step process here. We first need to find the derivative and then evaluate the derivative at x equals 1. That will give us the slope at x negative 1. That'll give us the slope at x equals negative 1. Once we have a slope, then we can use point slope form to write the equation of the tangent line. So let's see f prime. F prime is what? Okay, product rule says you take the derivative of the first function. So the derivative of x squared plus 1. Then we're going to multiply by x minus 2. Now, do note here, I mean, I've said this many times, you know, this notation right here, a capital D with a subscript x with brackets, means take the derivative of whatever's inside. Okay? So just make sure you're very intentional when you're writing out these, writing out your steps here, because, you know, obviously parentheses, that's just the regular function. A d subscript x, d sub x with the function in the brackets, that means we're going to differentiate that in the next step. So derivative of the first times the plain second function plus derivative of the second function, x minus 2, times the plain first function, x squared plus 1. Okay. And now we just need to take these two individual derivatives. So the derivative of x squared is 2x. Derivative of 1 is 0. So we have 2x times x minus 2 plus, we have the derivative of x minus 2. Okay, the derivative of x is 1. Derivative of negative 2 is 0. So this derivative is just 1 times x squared plus 1. So I suppose I don't usually do this because it require more work and it's not necessarily super helpful. But here, it's not just a little bit of work here to distribute and collect like terms, and it will make this one look a little better. So I'm going to distribute here and get 2x squared minus 4x, and then we don't have to distribute really at all here because it's just multiplied by 1. So plus x squared plus 1 plus x squared plus 1. And so we have 2x squareds and 1x squared. So that's 3x squared minus 4x plus 1. Okay. Now, I guess we could verify that if you want to. We could verify that and show that that's the exact same answer you would get if you first distributed the original function. Here, so let's do this. Let's just, since we're not in any rush here, it won't take a sec. Let's distribute FOIL. So x squared times negative 2, so that's negative 2x squared. Then x squared, oh, sorry, I forgot, I guess it doesn't matter. But if we're going to FOIL that, I didn't do that right. So I don't usually like to use the term FOIL, but it's fine. It gets the job done. So let's see here. x squared times x is x cubed, rather. And then x squared times negative 2 is minus 2x squared. Then we have 1 times x, so that's plus x minus 2. So that's the original function just rewritten. So that's f. No calculus there. So if you want to verify that our answer is correct, well, let's differentiate using this other version of f. Okay, so now we don't have to use the power rule. Sorry, we don't have to use the product rule. We can use the power rule and say, that's okay. The derivative of x cubed is 3x squared. The derivative of, okay, so we have a constant multiple negative 2 times x squared. So we can differentiate x squared and get 2x times negative 2 would be minus 4x. The derivative of x is 1, and the derivative of negative 2 is 0. So yeah, we get the exact same answer. So it's always nice to see that you can work this derivative question 2 different ways. But remember, we're not done. That's just the first step here. Because the question here is not to find the derivative. The question here is to find the equation of the tangent line at x equal negative 1. So if you want the slope at x equals negative 1, the way you do that is to evaluate f prime of negative 1. So you find the derivative and you evaluate negative 1. So let's see. In both cases, we have the same answer for f prime. So you have 3 times negative 1 squared minus 4 times negative 1 plus 1. So what? That's negative 1 squared, of course, is positive 1. So we have 3. Negative 4 times negative 1 is positive 4. So plus 4 plus 1. So I guess that looks like 8 to me. Okay. So we have a slope of 8. So this is, we call it m when we use point slope form. That's our slope. Now we have a point. All we're given is the x value. But remember, to find the y value, you evaluate the original function. So that's just algebra. If you want to find the y value that corresponds to an x value, you look at the original function f. So what do we get when we plug in negative 1 into f? Okay, if you plug in negative 1 up here to the original formulation here, we have what? Negative 1 squared is positive 1, plus 1's 2. So we have 2 times negative 1 minus 2. So that's what? Negative 3. So we have 2 times negative 3. I guess it would be negative 6. Oop. Would be negative 6. Okay. So let me double check that real fast. Plug in negative 1. That would be 2. Yeah, that's good. Okay. So we have a point. We have a slope. And now we can use the point slope form, which is y minus y1 equals m times x minus x1, where that's x1 and that's y1. Okay, so we go over here and we say y minus y1. So y1's negative 6, so minus negative 6 equals m, which is 8, times x minus x1, which is negative 1. And now we clean this up a little bit. Let's see, that's y plus 6 equals 8 times x plus 1. And we want to solve this and put it in slope. I mean, this is the answer. I didn't specify in the directions here. So this is the answer. But on a test, I'd probably say write this in slope-intercept form. So it's a good habit to be in. So, y equals mx plus b form. So if we distribute 8x plus 8 and then subtract 6 from both sides, we get what? Y equals 8x plus 2. And there should be our answer. Let's double check it. Let's use Desmos. Here, let me type the function really fast. So the original function is f of x equals the product of x squared plus 1 and x minus 2. And then our point is -1, -6. Okay, and then our tangent line we said was y equal 8x plus 2. And let's take a look. Okay, it looks good to me. So the red is the original curve. It's a cubic once you multiply it all out. Nice cubic curve. There's the point -1, -6. And the green is our tangent line. So the red is the original curve. There's like this blue point here, and then you have the green tangent line. So it's really important. I really encourage you to always do this. I don't always do it just for time's sake, but I'd encourage you to always do this because it's really important that you can visualize what a tangent line looks like. So, like if I just told you, there's a point on this curve, I want you to be able to visualize what the tangent line would look like. Would it be, on the left side or the right side? What would the slope generally be? Would it be a positive slope? Would it be a negative slope for that tangent line? How steep would it be, generally speaking? It's good to be able to visualize that in your head. And what it takes to get that skill is just to practice it. See a bunch of them. Desmos is a great tool for doing that. Okay? By the way, notice, this wasn't the question, but there's a horizontal tangent line. Looking at the next question, there's a horizontal tangent line here at this trough and at this crest, that peak. That's where there's horizontal tangent lines, where there's little peaks and valleys. Those are the horizontal tangent lines. Okay? All right, let's look at this other question. The other one is our other, typical question that we're going to ask a lot, which is determine the location of horizontal tangent lines. Now, there's any function's not guaranteed to have a horizontal tangent line. So, by the way, it is possible there's no solution. But we are always interested in, first of all, knowing if there are any locations of horizontal tangent lines. And if so, let's find where they are. Okay? Our general strategy here was to find the derivative, set the derivative equal to 0, and solve. So basically our strategy, if you want to put it in one step, is solve f prime, g, we're calling this function g, solve g prime of x equals 0. That's our method. Put it into one step. Solve g prime equals 0. Okay? So of course that means we need to find g prime. This is a quotient of two functions. So quotient rule is required here. I don't see a way to easily rewrite that to where it's not a quotient. There would be a way if we have what's called the chain rule, but we haven't covered that yet. So for right now, we're going to use the quotient rule. So quotient rule, remember you write your big fraction bar because it's going to be a pretty big deal here. Funiculum is the word for that. So we do the derivative of the top function. Derivative of the top function, which is 16x, times the bottom function, which is x squared plus 16, minus the derivative of the bottom function, which is x squared plus 16, times the plain top function, 16x, divided by the bottom function, x squared plus 16 squared. Okay, so that's what the quotient rule tells us to do. And please don't skip that step. If you try to skip that step, you're gonna get messed up. You're gonna make an error somewhere, and then you're gonna do all this work and get the wrong answer. So do not skip the first step when you're writing out what the quotient rule says. Same thing for the product rule, like I did on the last example. Okay, all right. So now we're gonna take those individual derivatives. We're gonna need that fraction bar again. So the derivative of 16x is 16. 16 times the existing x squared plus 16 minus, okay, the derivative of x squared is 2x. Derivative of 16 is 0. So that's going to give us 2x times 16x. Okay? All divided by x squared plus 16. There's really nothing to do on the denominator. No reason to expand that or anything. Now, we've differentiated now. Since this won't take much work, I will distribute and collect like terms on the numerator. Since, again, it doesn't really take much work to do that here. And that's going to be necessary anyway because we're about to solve this derivative set equal to 0. So we will need to clean up the top anyway. So let's see. 16, distribute here, 16 times x squared. That is 16x squared. 16 times 16, that is what? 256, hopefully. Then we have negative 2x times 16x. That's going to be what? Negative 32x squared. All divided by x squared plus 16 squared. And now collect a couple like terms. And we get what? 16x squared minus 32x squared. That's going to be negative 16x squared plus 256 over x squared plus 16 squared. So there is our cleaned up derivative. Of course, we're not done. That's just the first step, because what we want to do here is solve the equation g prime equals 0. So let's do that over here. G prime equals 0, so that is negative 16x squared plus 256 over x squared plus 16 quantity squared equals 0. Now, I get a lot of students, when they see this for the first time or see a similar question for the first time, are super confused. Don't know how to solve this, okay? But here is a very important tool, or just a concept you need to file away, and because you're going to see this kind of question all the time. A rational function set equal to 0. When you have a rational function set equal to 0, all you have to do is set the numerator equal to 0. Okay? Why? Think about it. If you have a fraction, what is the only way a fraction can be 0? The only way a quotient, a fraction, can reduce to 0, simplify to 0, is if the numerator is 0. That's the only way. So we can boil down this problem to simply saying, where is the numerator equal to 0? So we can say negative 16x squared plus 256 equals 0. That is the solutions to the original statement will be the solutions to the numerator set equal to 0. So always think about that. A rational function set equal to 0, or not even just a rational function, a quotient of two functions set equal to 0 will only be 0 where the numerator is 0. We'll need to use that fact all the time, so make sure to file it away in your head. Okay, so now that's just a quadratic. We can solve that, a dozen different ways. I think the square root property will probably suffice. Let us add 16x squared to both sides, so we get both sides positive. So we get 16x squared equals 256. Okay, if you want to use the square root property, the general strategy is to isolate the quadratic term, so divide both sides by 16 here. So we get x squared equals 16. And now we can take the square root of both sides, and we get x equals, don't forget this, lots of students forget that when you take the square root of both sides when you're applying the square root property, is you have to use a plus or minus, because there is a positive and negative solution. Basically, that's due to the fact that the square root of x squared, there's two possibilities, a negative and a positive, so you have to account for both. Okay, so simplify here, x equals plus or minus 4. And there we have our solutions. Okay, again, it's probably a good idea to verify graphically. And just, again, if you're always looking at graphs, you'll have a much better experience in this class. You'll get much deeper understanding. So let me type in the function real fast on Desmos, then we'll take a look to make sure our solutions are correct. That there is indeed a horizontal tangent line at both -4 and +4. So 16x over x squared plus 16. And there we are. By the way, I don't know if I mentioned this before. Desmos will, you've probably noticed, Desmos will identify those locations for you. Now, if it's an irrational number, it'll give you a decimal approximation. But notice that if you just kind of click on the curve, it does identify that 4 in the y value is 2, and -4, y value is -2, are the locations of horizontal tangent lines. So if I do that for any function, if I change the function a little bit, notice it kind of gives me that peak, that gray point. I changed the function, but it still identified it for me. So remember, your horizontal tangent lines graphically are where you have little peaks and little troughs, a trough or a valley. Okay, so crests or a peak, and troughs or a little valley. Notice that's where the function changes from falling from left to right, decreasing, to increasing, rising from left to right. So there's a little valley there where we're changing from a negative slope to a positive slope. And if you change from a negative number to a positive number, you hit 0 in between. And likewise up here, we're changing from a increasing function, a positive slope, to then a negative slope to the right of that peak at 4, 2. So we're going to talk about this extensively throughout the next chapter, but it's good to get this in your head already. Okay, so again, those are our 2 very important applications in this video: finding where there's a horizontal tangent line, if any, and then of course the other application, which was finding the equation of a tangent line. So 2 very important processes. Make sure to really practice each a lot. If you have any questions, don't hesitate to reach out. I'll catch you in the next video.